Cast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to today's TracePro webinar. Our webinar for today is going to be how to do Monte Carlo tolerancing using TracePro's 3D Interactive Optimizer. Our presenter this afternoon is going to be Mike Gauvin, our VP of Sales and Marketing here at Lambda Research. My name's Dave Jacobson. I'm the Senior Applications Engineer here, and I will be acting as the moderator this afternoon. One quick note, if anybody has any questions during the webinar, please feel free to submit them using the questions box in the GoToWebinar control panel, and we'll look at all the questions at the end of the webinar. So with that, I'm going to turn it over to Mike. Mike?
Thanks, Dave. Okay, so let's get into how to do Monte Carlo tolerancing in TracePro's 3D Interactive Optimizer. So our agenda is the intro to the 3D Interactive Optimizer and where you're going to find the tolerancing capability. I'm also going to talk about the algorithm behind the Monte Carlo tolerancing. I'm going to show you how to set up a tolerancing analysis in the 3D Interactive Optimizer and then how to run it. I'm going to walk through three examples: a simple switch with LED placement, a Luminaire Par 38 example is the third example. So what do these systems look like? Well, first of all, you can see the two examples that we're going to use on the side there. And we're going to set some goals here. I mean, what can you accomplish with a Monte Carlo tolerancing analysis? Well, you can check on changes due to manufacturing processes. You can look at possible installation errors and how they will affect the end result. Finally, you're going to get an idea of how the system will perform after manufacture. So if you're manufacturing thousands of these, how are those components going to perform over the many iterations of the manufacturer process? So let's start off with an introduction of the Monte Carlo tolerancing capability. The Monte Carlo tolerancing capability is available from the 3D Interactive Optimizer. So you're going to have to launch the 3D Interactive Optimizer. You're going to go into the optimization dialog by selecting the operation mode tolerance analysis, as you can see down there. And that's different than, say, looking at, for instance, the optimization process, which is one of the operation modes. Well, what's the algorithm behind the Monte Carlo tolerancing capability? The code behind the Monte Carlo tolerancing comes from Oslo. It's been used for over 30 years for doing Monte Carlo tolerancing on all types of systems. Now, a Monte Carlo analysis uses random numbers to generate a sequence of lenses, light pipes, or mirrors, whatever kind of system that you're working in, where the maximum magnitude of the perturbations is determined by the current values of the tolerances. So for all the variables that you set, you're going to set a lower and a higher limit, and you can also use user-defined variables, and the system will be perturbated from the lower to the higher limits randomly on each one of these iterations that's being done for the Monte Carlo analysis. Each random realization will construct the lens with those parameters, or the light pipe, or the optical component. And you're going to then do a full analysis in TracePro, where we're going to keep all the results for later post-processing and to show you what the full Monte Carlo analysis is graphically. So the advantage of using this Monte Carlo type analysis is that all the construction parameters are perturbated simultaneously. So for each iteration, you may have 5 variables, you may have 10 variables, all of them will be changed and you'll get a different result. So of course, you're going to want to do a lot of trials. So the analysis of the performance of the resulting system provides a statistical prediction of the distribution of the final fabricated optical components as you go over time. Because of the stochastic nature of the process, depending upon the optical component and its sensitivity to its construction parameters, the Monte Carlo analysis may converge slowly to the true value of the performance statistics. So if you're producing thousands of different parts, you might want to do a couple of hundred trials in terms of iterations. So, to really cover what's going to happen, for the manufacturing process. Also, since all of the parameters are varied simultaneously, it can be difficult to locate which parameters are the most sensitive. So, changing what component is going to create the largest discrepancy. Well, one of the good things about the TracePro Monte Carlo tolerancing capability is that all iterations All iterations are saved for post-processing. In other words, you're going to specify where a subdirectory is that you want all the results to go to, and you can look at them to your heart's content after you've done the Monte Carlo analysis. So this can be very useful in evaluating both optical and illumination systems. So let's look at an example. Let's jump right into it. Let's look at a light pipe switch. So in this light pipe switch, it's really a very simple system, and I wanted to start off with a real simple one. You've got an LED, it's on a printed circuit board. There's this light pipe made out of plastic, and then you have a target. Now the light pipe has both an entrance area where the LED will emit into, and then hopefully be focused into that second area where it will come out collimated to the target. These are light pipe switches that are used in cars to give information to the driver where you push them in or pull them out, and they have something stenciled on them so you know exactly what that particular operation is. This could be anything from turn my lights on to is the radio on, or I want to turn the radio on. It's just a button switch. Okay, so what we're going to do is that we've defined a target, an LED, and a switch, and we're going to perturbate that light pipe switch by changing the inner area. Okay, now that we've got that and we know what we're going to be doing here, we go into the interactive optimizer and we're going to set up the profile of that light pipe. So in this case, as you can see, we've got this inner area and it's defined by several control and segment points. Now this is a symmetric profile, so anything I do to the bottom will also be done on the top. So in this case, when I change the controller segment point up on the top, it's also going to happen on the bottom as well. So I only have to set up two variables. This is really nice and quick. Now, if you wanted to, you could set this up as an asymmetric profile. And in this case, you would be able to change the bottom and the top. So they would change differently. But pretty much in the plastic injection molding process, due to the thickness of the different materials, this is where you're going to have a discrepancy. It's either going to melt a little bit more and or not melt a bit more. You've got humidity conditions, you've got temperature conditions inside the building where this happens. That's what's going to change these parameters. So these are the couple of things that you might want to look at, that during the manufacturing process, those control points move around a bit. And because of that, you get a different shape for that entrance aperture. That's what we're going to tolerance here and see how that affects the flux on our target right in front of the light pipe. So what we have to do is, after we've created this profile and we've pulled on the control and segment points, we want to set that control point, which is the green little dot there, to vary. And we want to set the segment point, which is the the orange dot, to move around. So here you see in the interactive optimizer how I pulled on these points, and now I'm going to go to the point where I'm going to make them vary. To do that, I go into the property editor. I select, for instance, either the segment point or the control point, and it's going to come up that in the third column, it says specified. We're going to have to change that to an absolute variable, and then we're going to specify a lower and an upper limit so that we can tolerance that particular value in between. So here you can say that we're going to be changing in the Y position that variable to go from 2.8 to 3.2 for the segment point, and from 2.6 to 3 for the Z position of that segment point. So that's how we set these up as variables for the tolerance analysis in the property editor. The next thing we're going to do is we're going to bring up the optimization dialog. This is where we're going to specify a path that all of our resultant files, all the results, all of them will go into that particular subdirectory. So we can keep this separate. We know exactly what the name of this is. So this is a temporary iteration type area that I've created, which is what the name of the path is, temp iter. I've given a prefix. You can name it whatever you want. So in this case, I'm going to call it SS. You could call it TT, whatever you want to, just so you remember that if you're doing multiple tolerances analysis, those are the files that have that particular one. Finally, you're going to have to change that operation mode to tolerance analysis. And now that you've set all those variables in the property editor, they're going to show up in the variable list right over here. Since we're changing the Y and Z position of the segment point and the control point, we're going to have 4 total variables. So you can see their current value that's sitting there in column number 5. You can see the lower and upper limits, and you can see the distribution that we're going to use for this. There are 3 different distribution modes. I'm using uniform usually I always use uniform for tolerancing, but there's also endpoint capability distributions, and more. In the bottom here, you see the object list. In the object list, this is the part you're going to create for doing all this tolerance and movement. So that's going to have the switch. It's going to have a material property assigned to it, and we're pretty much ready to go. This is all we had to do to set up the optimization dialog. So now we hit the start button at the bottom right of the optimization dialog. We wait a few seconds, and the tolerance analysis dialog is going to show up. This dialog is going to ask you how many trial iterations that you should do. I'll tell you that you should do at least 100, and that's what I'm going to start off with here, 100 trial iterations. And how am I going to be able to tell if 100's enough? When we look at the results, it's very easy to see. So as it starts chunking through these 100 Monte Carlo trials, an optimization log is going to appear. And the optimization log will show each iteration row by row. So we're going to see 100 of these different IDs or iterations. There's going to be an error function in the second column. There's going to be the set of variables. So we have 4 variables. There's going to be 4 different values here, one for the YZ of the segment point positions and one for the control point position YZ. Finally, in the final column, it's the time, which is how long it takes the iteration to run in TracePro. This takes about a total of 15 minutes. In the bottom of the optimization log is a trend chart or a graph. I've got trend chart picked right now, and you can see that over the 100 iterations, what the error value is over each one of those iterations. So there's your graph that shows you the error function for each one of the iterations, 1 through 100. And you can see it's jumping all over the place. So what I'd like to do is to see that result in a nice graph. So here is the nice graph. So this is the Monte Carlo tolerance analysis for 100 trials for that switch. On the bottom is the error value. Now we didn't move that particular opening very much in the light pipe switch. And so because of that, the error value doesn't change very much, about 0.02 across the whole 100 iterations. So this figure is pretty much the error value versus accumulated ratio. You can see that the majority of the results for this analysis are in the 0.5853 to 0.5953 range, which has about 75 results. How do I know that? At the top of each one of the bars is a red number. That's the number of iterations that fall into that error value range. And we add them up, and there you have them at the top. If you add all those red numbers up, it should equal 100. So there's 75 in the middle. And that's exactly what you expect. As this thing moves around, you don't expect that you're going to go far away from your perfect design. Making changes is going to still keep you mostly in a very, very good range because this light pipe design is very simple. There's not a lot of things that are going to change. So your results should be very, very close to each other, even if you're making some changes in that middle area, unless they're drastic. If they're drastic, then you might see a lot of values outside the main region. So when we go from the tolerance analysis to the results, once again, what is this error function? Well, the error function is pretty much the total flux. In fact, I'm going to get into how the error function is calculated in just a minute. You also see all 4 of the variables for each one of the iterations and the time once again. And if you've changed from the trend chart to the graph chart, it then shows you what your operand is. Now for us, it was the flux on the target. So sure enough, it's going to show us on a luminance map anytime we select one of these iterations. We know when we've selected an iteration because that particular iteration will turn blue. So in this case, I'm showing the 100th iteration. And so that corresponding luminance map is the 100th iteration of this particular Monte Carlo analysis. Now remember I said that all 100 iterations are kept? They sure are. Wherever that subdirectory was, this is temp iter, there's all of those files. They're both saved as a text format and as a graph. So I'm looking at the bitmap file, and you can see it's SS_100, which means this is the 100th iteration. My SS was that prefix that I used, and this is a bitmap file I can view at any time. The corresponding text file run underneath it. That's if you want to bring it into TracePro, use your tools irradiance viewer to take a look at it there. In fact, you can even bring in 2 and subtract them from each other to see what the difference is. So these are the type of things that you can go through all 100 results, see how much things are varying as you go through them, and get a feel for what's going to be happening in the manufacturing process from one component to the next. And you may make some changes to your design if you think that things are changing way too much, and maybe that you're getting way too many components that are going to be thrown out because they're no good. So this is a way of taking a look at each one of them and finding out and having a good feeling for what's going on in your manufacturing process using the Monte Carlo evaluation here. Well, let's go one step farther. Let's go to a light pipe switch which moves the LED position. We're going to keep the old example, but we're going to add one new thing here. So that LED is going to move back and forth in the Z direction. So that means that maybe we have some glue that we've added to the PCB board to make sure that this particular light pipe sticks onto, and that's got a thickness to it. And we don't ever know what that thickness is. So we're going to move it back and forth, and let's see what happens with that, okay? And this will allow us to have 5 variables now, because we'll have the control and segment points Y and Z position, and now we'll have the Z position of the LED as well. That gives us a total of 5. So if we start doing the same thing we did before, we would add the control and segment points, and they're already there. But the fifth, this new 5th variable, is a user-defined variable. So I go into the variable list, I right-click, and I say add a variable. And I specify it's a user-defined variable, and I specify an absolute value. My value of 0 says it's exactly in the same place as it was before in my TracePro model. And then I'm going to make it go back and forth by specifying a low and a high limit. So there's your lowest value and your highest value that this possible LED can move back and forth. Over here in the operand list, you can now see there's my flux operand. So on my target, I'm looking for a target value of 1. Okay, whatever it is versus that 1, that's going to create my error function for me. And I'm going to talk in just a second about that. Finally, I want to use that user-defined variable to move the LED in my TracePro model, not here in the interactive optimizer, but in my TracePro model. To do that, I'm going to have to use the scheme language that's built into the interactive optimizer. So that's where that preprocessor object name is my after scheme command. Okay, so this gives us 5 total variables. We've got them all set up in terms of lower and higher limits, and we have an operand list. So let's get to the scheme macro language. It's a very simple macro. And the reason why it is that if we go back and take a look at this particular system, you're going to see it's just an LED, it's a light pipe, and a target, and a PCB board. So there's only 4 different things that I can perturb here. But I'm going to even make it simpler. What I'm going to do is the first command may not make sense at first, but it will in a second. It's going to be to delete the LED object. The reason why is that I'm going to create an original LED object that always stays in the same place so that I can move it back and forth using a move command. But I want to make sure that an LED original object always sticks around so I can use it each time during the iteration. So what I'm going to do is I'm going to call it LED_original, and I'm going to turn the ray trace flag off on that particular object. Then I'm going to copy it. And because the ray trace flag was set off, I need to turn it on, so I'm going to be able to trace this LED when I move it around. So that's what the next command does. The final command is the one that moves the LED using my user-defined variable Z position. So there's it. It's a very simple 4-line command. And now that first command, delete LED, makes sense because I'm taking the LED original each time, I'm copying it, moving it into place, and then on the next iteration, I delete it so I can create a new one and put it in place. And the LED original is always with the ray trace flag off, so I don't trace it. So the only thing that gets traced is the LED that gets pulled around. Its name is LED, and that's pretty simple. So once again, I'm going to start the analysis by setting the number of trials when I hit the start button. Sure enough, you can see I've entered 100 over here again. We've done this before in the first example. So now, once again, the tolerancing log of the 100 Monte Carlo shows up. There's the trend chart. There's the error function, which is sitting over there on the left, the iteration count on the bottom for all 100. And for instance, I've selected the 73rd one, which happens to be the best iteration. The reason why I can see that is that the error function is shown in red, and so is the time. And because I selected, there's a blue in the variable area. So now I've got 5 different variables. The first one is my position. And why do I know that? Because over here, we can see that the first variable in my optimization dialog is Z position. The next one is my control point for position Y. My next variable is my control point for position Z, and then my segment points in Y and Z. So now we go back over there, and we come back and we know exactly that's my Z position, that's my control point X, Y, and Z, and that's my segment point Y and Z. And then once again, the time it takes to run that iteration. Well, I've been talking about this error function. What is the error function? Well, it's different for each operand type and system. So for instance, if you're using a flux type of operand, which we are using in this example, the first two examples, the error value will vary across a range less than 0.02 because we're not moving that inner points very much, and we're not moving the Z position that much. But this is not always the case. But for this example, if the LED emits 1 lumen and 0.4 lumens reaches our target, then the error for this iteration will be the absolute value of the amount of power emitted minus the simulated flux on the target, or 0.6. So this is very simple. That error function is just 1 minus the power on every single one of these iterations. So your largest error function will be the least amount of flux, which is just the opposite of what you would think because it's 1 minus, and vice versa, your smallest error function will be the most power that you will get on your target surface. So what's best to get a good error value is that you set the target value of the operand very reasonably. So for instance, if the simulated flux is in the range of 2 watts to 5 watts, then you want to set an operand target of 5 watts or 6 watts, not 10 watts or 100 watts, because you're going to get very, very small values. Now, if you start thinking about this, how do you figure out what that number is going to be? What's your target value? Well, before starting an optimization, we suggest that you run a simulation. You can do that from the interactive optimizer by saying create model and run command ray trace. And it'll go off and do that. Then you can see the flux, and then you can see what you should be setting your target for the operand. It's that simple. Well, what about other types of operands, like for instance, irradiance or candela profiles? Well, the calculated error will fall into a range between 0 and 2, depending on how similar the simulated profile is to the operand profile. And the method that we use here is called the Pearson correlation coefficient. For colorimetric operands, such as CIE XY and CIE UV, the error is the distance between the target and the simulated color on the color gamut. And for the uniformity operand, the error will be determined by the formula defined in the uniformity target definer. What does that mean? Well, if I bring up the 3D optimizer, and I bring up that particular system that we've been using, so there's our switch, there's our property editor over here on the right, there's the object view which has the complete object created, and we go into our optimization dialog by clicking on the optimization menu. We can see all of our operands. They're over here on the right hand side. You can see that each one of the types are different in terms of what their input is, but the one that we just talked about is uniformity. And we go into the target value, it's going to pop up the profile definer for that particular uniformity, and it's going to ask you how you want to create the uniform, a uniform or a specific set of targets that you want to define. And the equation for the operand is shown right down here. There's your equation, and that equation is what is going to specify what your error value is. And you can define these on your own. You can move these targets around, whatever you want to do for uniformity, it's up to you. And that's how the error value for that particular function gets set up. Now, the one that we did was flux. And that flux that we did, that operand, is on the look here surface. Well, that look here surface is in the system tree of your TracePro model. It's the name of a surface. It needs to be the only name on this surface. It can't be anywhere else. You can't have 2 or 3 look here's. The program will get confused. And you need to then go back and type it in exactly like it is over here for the surface for the target. That way, when TracePro is doing the tolerance analysis, it knows where to get the information to feed back to the interactive optimizer so that the target values that you have are correct. Finally, you need to put a target value in. Well, we know because this particular LED has an emission surface, it is emitting 1 lumen. So our target value when you ray trace this is going to be about anywhere from 0.4 to 0.6, depending on the shape of the light pipe and everything else that we use. So a good target value would be 1. So now the error function will be 1 minus whatever the simulated result is. And that's what the error function will be shown in the tolerance analysis. It's that simple. So finally, let's go on to the next part of this. What are the results from this second example? Well, once again, you're going to see that we have a little larger range because now we're adding in the movement of the LED along the z-axis. We can see that once again, we're still in the same area and we still have very good results and there's still pretty much not much change. And we've got some very good, I got a very good feeling here that when this gets done, 100 trials is sufficient to show me what's going on during the production process with these different components. So there's your answers. And once again, we can go back into the Monte Carlo iteration optimization log. If we choose the 75th iteration, it's a little bit away from the 73rd one. The 73rd one shows the best result. The 75th is a little bit off of that. You can see that the variables have changed. The Z position of the LED is at 0.46, whereas the optimal position is shown in the variable list of the 73rd, which is 0.2296. So we look over here and we see that the flux is about 0.36953 lumens when it's on the 75th iteration. Well, I know all of my results are sitting in my tolerance position path. That's where I set this particular tolerance analysis up. And if I look at the 73rd, which is the best, I can see that at the Z position of 0.229 millimeters above the PCB board, it's 0.3835 lumens. So I have more power. Therefore, that is my best system. That's my best error function. So the best error function, the best amount of power and everything else is over here. It's the bottom. That's your most power, and the top over here on the right is the least amount of power. So usually when we do this kind of system, your power should be right around the perfect design area. Okay. What we also notice is that maybe moving the LED a little bit closer will give you more power. And that's another thing that this Monte Carlo analysis showed for us. Now, finally, let's look at the third example. This is a luminaire and lens shape example. Well, here we've got a bridge lux LED array, we've got a faceted reflector, and we have a plano-convex lens. There are 15 steps and rings in this faceted reflector, so it takes a little bit of time to create in TracePro, but you can see it's very nicely set up as hexagonal faceted segments. So we're going to go back into the interactive optimizer. We're going to put in the two things that are going to change in this model. That would be your reflector and your lens. And then we're going to create these creates two surfaces. One is a lens object and one is a surface object with the reflector. We're then going to go, and after we've created these shapes in our object with the correct 15 rings and the 15 segments, we're going to go back and specify that the lens control point is going to vary 0.1 millimeters in both the Y and Z direction. The reflector control points, there are 4 of them, we're going to allow them to vary up to 1 millimeter in both the Y and Z positions as well. So this is going to give us a total of 10 variables that we then need to go into the property editor and do the same thing we did before, which is to change them from specified points to relative or absolute variables, and then specify how much they can move back and forth. In this case, these are relative variables, and I'm allowing them to move 1 millimeter in both directions. Now, what's a little bit different here is that when I use a relative variable, it's going to keep moving it from the point that it last was iterated at. So you could move it a lot more than 1 millimeter in both directions, which is why usually when I do a tolerance analysis, I use absolute variables and not relative variables. But I wanted to show you this is something you may not want to do. And I feel a lot more comfortable when I'm using absolute variables. But let's see what the tolerance analysis did for this particular example. Okay. Well, when I go into my optimization dialog after I've set all 5 of those different points to vary, 2 on the lens and 4 on the reflector, I have a list of 10 different variables in my variable list. The next thing I also show you is that I'm once again selecting tolerance analysis mode in the operation mode. I'm specifying the path as tolerance webinar this time. So I've changed it 3 times so I can keep track of all these different files. And I've also put a prefix of reflector and lens, REFL and lens, as my prefix for each one of the files. Over here in the operand list on the right, you notice I don't have just one operand anymore. I'm using 3, beam width, flux, and uniformity. So this is going to be interesting how the error function is going to be created for this, because it's going to use all 3 and add each of them together to give me a final result. Finally, on the bottom here, I've got my object list, which then defines that I've got a polycarbonate plastic lens for my radially symmetric plano-convex lens. And I have a reflector that's going to be created as well. And this is going to be my two objects. I'm going to hit the start button. I'm going to specify the number of iterations, 25, and I'm going to let the program start doing all 25 of those trials. Now, this is a really good example because you see a lot of missing information here on both the left and right side. I've got a whole chunk of area that has no error values in it. And that's because I didn't put in enough trials. 25 is just not enough. And so I just wanted to show that to you, that you can see that there's only 1, 2, or 3 pretty much iterations in each one of these that match the error value. In fact, I think the largest is 4. Yep, it's right there in the middle. But also notice that the error value is quite large. We're going from 903 to 1013. That's because we're adding the error function for each one of those 3 operands. So when we go back, we're seeing that we're adding in the error function for the beam width, the flux, and the uniformity. So this is going to be difficult because one of the things is you're going to have to make sure those targets are at a good value so that when you add them up, they have meaning, so that they're all equal. They should be all about equal. So if the beam width is the most important in that terms of weight, the uniformity is important, you're going to want to add that in. Okay. So there's our error function. You're going to notice that the majority of the results of this are in the 936 to 969 error range. So pretty much we're in the middle. So the system is going to work very well most of the time. But in those 2 white areas on the very ends there, we're going to see that if we don't meet spec on these particular parts, for 25 different parts that we make, we're going to have to throw 5 parts on the bottom end. I'm going to have to throw 3 parts away on the top end. So this means that we have 8 parts that are going to fail out of 25, or a total of 32 out of 100 if we're making 100 of these parts, which is probably not going to be acceptable to anybody out there. So this is what the Monte Carlo tolerancing analysis is showing us for this particular example. And once again, we've got all the information here. Now you're going to see 10 variables shown in the variable list. You're going to see the error function for each one. And you can look at each result separately, either in the optimization log, or once again, we saved all the files. Now there's going to be lots more information here. There's going to be multiple BMP files. There's going to be multiple text files because we're saving the beam width, we're saving a luminance map, and we're also saving a uniformity map. So you'll have all that information here. Once again, you can go back and look at all 25 of the iterations and see what the information is for every single one of them. Once again, you've got the reflector and lens as the prefix of the file name. You've got then the iteration, and then you've got whatever that particular output is. In this case, a irradiance target is an irradiance map. A candela target is a candela map. Okay. Well, that's all for the Monte Carlo ray tracing, but I wanted to thank you all for attending, so I'm going to give you an Easter egg. There is also another new feature in the 3D Interactive Optimizer, the slider wheel capability. How do you use it? Well, if you've ever designed slider wheels in the Interactive Optimizer before and you know about them, you just have to go to Window Slider Wheels and it'll pop up. So let's take a look at one. The slider wheel control in the dialog here has a lot of information. The first column is going to specify what surface the slider wheel is on. The next bit of information tells you if it's a control point or a segment point and which segment it is on that particular control point. It's then going to allow you to look at, is it a position Y, is it a position Z, a position X? Then that value is there. So you know where the slider wheel is going to be and what's going to be changed when you change it. The next thing is that wherever that particular, in this case, control point is, it's going to show you that value. And that's shown there, directly entered. And to change that value digitally, you can slide the slider bar backward, to the left and right. And how much you move it, the tick, is going to say how much that's going to particularly change. In this case, the value is 0.6. So if I move the slider bar one tick to the right, the value is going to change to 4.648. If I change it in the other direction by pulling it to the left from the 4.04, it's going to be 3.4. So you can change the tick to be very small. You can change the tick value to be very large and just move these back and forth. Well, how do you set one up in the Interactive Optimizer? It's 7 steps. You create the geometry. You select any control or segment point on an object. In the property editor, you can see that particular value. You then change the type from specified to either relative or absolute variable, and then you enter a lower and an upper limit. Okay? Once you've done that, this is the most important point. You go to the description field and you right-click on it. When you do, you'll see a pop-up that says Add as Slider Wheel. Click on it. When you do that, the slider wheel dialog menu will show up. Now you can drag back and forth to change the geometry, you can change the tick value, and you can start seeing in the Interactive Optimizer what happens when you change that particular segment point by using the slider wheel. So here's an example for you. We've got that particular segment point up on the right-hand corner, and right now the position of that is 7.755. If we start dragging it back and forth, that allows you then to change that position and see what's going to happen. Now, you probably want to have traced some rays, so inside of here, and then while you're pulling it back and forth, see what the effect is by changing it. And that's pretty much what I would expect for using the slider wheel control. So there's your Easter egg for attending. And the last slide here, we're going to talk a little bit about conclusions of using the Monte Carlo tolerancing. So I think a Monte Carlo tolerancing is very beneficial. It's very beneficial because it shows how a system is going to perform due to manufacturing errors. So you're going to find out how well the system is going to perform, say, for the LED moving around, for some shrinkage or something going on in your plastic light pipe, as we saw in the first 2 examples. Further, if you're buying off-the-shelf lenses, there may be some errors, some tolerancing errors on those as well. You can put those right into the Monte Carlo tolerancing analysis and do that 3rd example. You can and you should investigate the post-process results to get a feel of how your system is going to perform for each individual component. So you're going to get to see if that system is going to work well, or if you're going to have manufacturing problems and you're going to have a very bad failure rate. And like you saw in that last kind of system, there was a large failure rate if you had a very close spec in that middle area. Well, on those outside, you'd be throwing parts away, and that would be a bad thing. If that's the problem, if you get to that 3rd example and you realize that lens or the reflector is going to be a real problem for you, how can you solve that problem? Well, you might want to make the reflector a little bit different in shape, so it's not so easy to have it vary quite a bit when there's a tolerance error. So you might want to keep that in mind when you do your type of design, that you might want to design in a performance change that when the tolerance actually occurs, the system is robust enough to take that change. Finally, make sure you specify enough trial iterations. For the first 2 examples, 100 trials were very sufficient, and you can see that because we had entries in each one of the error value range. For the last one, 25 wasn't good enough. We saw large gaps, and I would feel very uncomfortable using that type of information and then trying to figure out just how good my manufacturer failing rate was going to be. So if you're going to be doing this and it takes a long time for your particular system, you have lots of variables, I'd say start it at 5 o'clock, come back the next morning. All the results are going to be there. The log is going to be there. In fact, what's nice about it, and what Dave pointed out today, is that when you bring up an optimization log, which is underneath the window over here, it has all the information. I can save all these logs and all the iterations by doing a file save as after the tolerance analysis is done, and it keeps all that information for me. So the log's there. I can go to any iteration. So I can go back to, for instance, the optimization log. I can click on any iteration, see the result, but I can also update the model in TracePro, redo the analysis, and see that analysis if I want to find out exactly what is occurring and exactly what changed that caused the problem that I'm now seeing in my Monte Carlo results of the tolerance analysis. So keep this in mind when you're doing the Monte Carlo analysis. Everything is available if you save after you've done it. And by the way, all those files are kept in that temporary directory. So that's it for today. I'm going to open up to the question and answer session, and I wanted to thank you for viewing this particular webinar. And once again, my name is Michael Gauvin. I'm the VP of Sales. You can send me an email at the email address there, or give me a call if you have questions on it. And please don't hesitate to sign up for a free 30-day trial if you're a prospect. We'd love to have you try out this new capability in the program. Dave, do we have any questions?
Thanks, Mike. Great webinar. You may want to pop up your last slide, because right now it's still showing the optimizer in TracePro, just so everybody wants to see your information there.
That's a very good idea.
As of right now, we don't have any questions, but I will put the call out. If anybody has any questions about the webinar today, please feel free. Just type them into the questions box in the GoToWebinar control panel. I should also let you know that we are recording this webinar, and the archive copy of it will be available on our website probably within the next day or so. So the slides as well as the recording and the video will be available. So I don't see any questions right now. And Mike, you answered the one that I would have had about showing them how to update the model based on the different iterations. So if there are no questions, I think we can probably wrap it up for this afternoon. I'd like to thank everybody for attending, and we do look forward to seeing you at the next webinar. Mike, anything to add?
Nope. Thanks for attending.
Have a good day, everyone. Bye.